Hello and welcome to Chapter 2, Discovering the Universe for Yourself out of the Essential Cosmic Perspective book here at OTC. Let's take a look at this chapter here. I'm going to try to make this short for you. Patterns in the night sky. What are we looking at? Our goals for learning in this chapter are the following. What does the universe look like from the Earth? Why do stars rise and set? Why do the constellations we see depend on latitude, where you are on the Earth, and the time of year? So with the naked eye, we can see more than about 2,000 stars, as well as the Milky Way. And then that dark stuff within the Milky Way is gas and dust. That's really it. Constellations. You know what a constellation is. You've seen constellations in the sky. But we actually have a definition for what a constellation really is and how many of them there are. A constellation is not just a set of stars, but it's actually a region in the sky. And there are 88 constellations that fill up the entire sky. Think of it as zip codes or area codes, state borders. So there are 88 of these borders. And so the stars that are all within the constellation of Orion belong in this box that's outlined here. Now, throughout the presentations, we're going to do some lessons called Think, Pair, Share. And I'm going to do a little twist on that topic here in the online course. So here's a thought question for you. The brightest stars in a constellation, do they all belong in the same star cluster? Do they all lie at about the same distance from Earth? Or may actually be quite far away from each other? What do you think? They actually might be quite far away from each other. We just see them in the sky, in the same place. So our concept or model of the sky is called the celestial sphere. And so stars at different distances all appear to lie on the celestial sphere. And the path that the sun takes along with the planets is called the ecliptic. It is the sun's apparent path through the celestial sphere. And it is tilted 23.5 degrees to the equator, the same tilt as the Earth. And so the 88 official constellations cover the celestial sphere. Now the Milky Way is a band of light that makes a circle around the celestial sphere. It is our view into the plane of our galaxy. So our galaxy is actually like a spiral galaxy. It looks like a hurricane, and we are out in one of the arms. We're in the Orion arm, and we are looking out into space. We are about 50 to 75,000 light years away from the, about 20,000 light years away from the center of the Milky Way galaxy. The Milky Way is about 100,000 light years across. So the local sky. We can talk about an altitude above the horizon and a direction along the horizon in your local sky. And the point directly above your head is called the zenith. We can use our hands to measure angles in the sky. And so you stick your hand out like this. If you put your thumb out like this, then your thumb covers about 1 degree. Your fist covers about 10 degrees. So you can go out during the day, look at the sun or the moon, and cover it up with your thumb, close one eye, because the sun and the moon both are about 1/2 of 1 degree. So in angular measurements, excuse me, there's a 360 degrees in a circle. In 1 degree, there are 60 arc minutes. And then each arc minute is divided up into 60 arc seconds, just like time would be. So why do stars rise and set? It's because the Earth rotates to the west, to east, so the stars appear to circle from the east to the west. Some of the stars never set because they are so far to the north that they are circumpolar. They never set below the horizon. However, there are some stars from Missouri that we cannot see because they are so far to the south. So why do the constellations we see depend on the latitude and time of the year? They depend on the latitude because your position on Earth determines which constellations remain below the horizon. They also depend on the time of year because Earth's orbit changes the apparent location of the Sun among the stars. So during the spring you see some constellations, during the winter you see other constellations. Now let's review on the Earth we have latitude and longitude. Latitude goes north and south of the equator. Longitude goes east or west of the prime meridian, which runs through Greenwich, England, close to London, England. Now the celestial pole is the point in the sky where the star Polaris is, our pole star, and this is where all the stars seem to go around. The altitude of that pole star, the Polaris star, is your latitude on the Earth. And for Springfield, we're at about 37 degrees north latitude. So Polaris is 37 degrees above your horizon. So in this section we learned that there are 2,000 stars we can see in the sky. Milky Way with our naked eyes we can see, and each position in the sky belongs to one of 88 constellations. We can talk about the altitude above the horizon and the direction along the horizon of an object. And the stars and planets rise and set because of the Earth's rotation, not because of this motion in the sky itself. Your location determines which constellations are hidden by the Earth, and the time of year determines the location of the Sun in the sky. During the winter time it's quite low, and in the summertime it is quite high. Now let's look at the reasons for the seasons. What causes the seasons, and how does the orientation of Earth's axis change with time? True or false? The Earth is closer to the Sun in the summer and farther from the Sun in winter. What do you think? Here's a hint. When it is summer in the United States, it is winter in Australia. The answer is false. The seasons are opposite in the north and south hemispheres, so distance cannot be the reason. The real reason for the seasons involves Earth's axis tilt of 23.5 degrees. So during the summertime, the Earth is tilted, the northern hemisphere is tilted more directly towards the Sun. We get more direct sun angles. During the wintertime, we get less direct sunlight on the northern hemisphere, where we are in Missouri. And I also said earlier, the sun's altitude changes with the seasons. It's higher in the summertime, lower in the wintertime. Let's take a look at this real quick. Why doesn't the distance matter? The variation of the orbit of the Earth is actually quite small, 3%. We are anywhere from 91 million to 94 million miles away from the Sun during a year. We are actually closer to the Sun, 91 million miles, in winter. Now that difference is about the same as this analogy. Let's say you were 30 feet away from a bonfire and you step 1 foot closer to that bonfire. Are you going to feel a lot more heat? No, you really won't feel anything negligible. So that's the same variation we see in our orbit around the Sun. Now we have 4 points in our orbit: the summer solstice in June, the winter solstice in December, and the spring and fall equinox. The tilt of the Earth's axis causes sunlight to hit different parts of the Earth more directly during the summer and less directly during the winter. We can specify the position of an object in the local sky by its altitude above the horizon and direction along the horizon. The tilt of the Earth's axis is 23.5 degrees, so season pattern is not affected. I will tell you that the Earth wobbles on its orbit, though, in a 26,000 year precession cycle that slowly and subtly changes the orientation of the Earth's axis, and also will change the northern star, right now Polaris, not going to be that way all the time. Alright, let's take a look at the moon. What causes the phases of the moon and what causes the eclipse? Lunar phases are a consequence of a 27.3 day orbit around the Earth. The reason for lunar phases is the orientation between the Sun, Earth, and Moon. Has absolutely nothing, not a thing to do with shadows. Half of the moon is always lit up. Half of it is always dark. And we see a changing combination of the two. So there are 4 main phases and 4 other phases in the cycle of the moon. We start with new and then go to a crescent moon, first quarter a week later, a gibbous moon, more than half lit up, full moon 2 weeks into the cycle, a waning gibbous, third quarter or last quarter, and then a waning crescent. It takes about 4 weeks to occur. And there are certain times of the day and night where we see the different phases of the moon. Now it is true we only see one side of the moon. This is caused because we have a synchronous rotation around the moon. It rotates exactly once with each orbit around the Earth. Okay, something different now. What causes the eclipses? The Earth and the moon do cast shadows. When either passes through the other's shadow, we have an eclipse. So a lunar eclipse is when the moon goes through Earth's shadow. And this can happen all night long for a large portion of the Earth. Lunar eclipses can only occur at full moon. A solar eclipse is when the moon passes between the Earth and the Sun and casts a small shadow on the Earth. Solar eclipses can only occur at new moon. And there are 3 types, a partial, total, and annular. We are going to have a total solar eclipse of the Sun in August 2017 in Missouri. You will have to go to Columbia, Missouri to see the total effect. And I will be there at Faurot Field, August 2017, when we expect 200,000 people to come to the campus of the University of Missouri at Columbia and see the eclipse from Faurot Field. It'll be awesome. We don't have an eclipse every new and full moon because the moon's orbit is tilted 5 degrees. And so there are times that we can see eclipses and times that we don't see eclipses. So in summary, 2 conditions must be met to have an eclipse. It must be a full moon for a lunar eclipse or a new moon for a solar eclipse. And the moon must be at or near one of 2 points in its orbit. We call these nodes, where it crosses the ecliptic and we can have an eclipse. So we can predict eclipses, and that one that's going to go through Mizzou is August 21st, 2017. And I can tell you, I know the astronomer up there at Mizzou, they are very excited to be hosting this event, probably the biggest event in the country, in the world, that day. Ancient mystery of the planets. We're going to look at why planetary motion early on was so hard to explain, and why the ancient Greeks rejected the real explanation for planetary motion. So we know that Mercury is very hard to see. It's always close to the sun in the sky. Venus, sometimes called the morning or evening star, is very bright when it's visible. Mars is noticeably red. Jupiter is very bright and big. And Saturn is moderately bright, a little bit less than Jupiter. Now, early on, we're talking thousands of years ago, planets usually move slightly eastward from night to night relative to the stars, but sometimes they do go westward or backwards in its motion, and Mars does this often. And this is called apparent retrograde motion, a backwards motion. It's similar to having 2 cars on the highway, and you look and you pass the car next to you on the highway, and it appears to be going backwards. It's the same thing. We're passing it in its orbit. Now, retrograde motion was easy for us to explain because this occurs when we lap another planet or when Mercury or Venus laps us. But it is very difficult to explain if you think that Earth is the center of the universe. In fact, ancients thousands of years ago considered this but rejected the correct explanation. They did think the Earth was the center of the universe. We later found out it was not. So, why did the ancient Greeks reject the real explanation for planetary motion? It was their inability to observe stellar parallax. Parallax is when you put your thumb out, you close one eye, you can cover up a tree or the sun or the moon, and you blink to the other eye and it moves. Now what moves? The object you're covering up or your thumb? Well, neither. It's your perspective you're looking at, and that's stellar parallax. So the Greeks, thousands of years ago, knew that the lack of observable parallax could mean one of two things. Either A, stars are so far away that stellar parallax is too small to notice with the naked eye, or B, Earth does not orbit the Sun, it is the center of the universe. And with rare exceptions such as Aristarchus, the Greeks rejected the correct explanation because they did not think the stars could be that far away. So thus, the stage was set for a long, long historical thousands of years of showdown between Earth-centered and Sun-centered systems. We'll get more into that as we go through these next few chapters.